Transmutations, the change of one element into another, involves a change in the nucleus. The number of protons gives the atom its identity as a chemical element. When the number of protons in an atom is changed, the atom is changed into another element. Transmutations may be either natural or artificial. Natural or spontaneous transmutation occurs in an unstable radioactive element which decays into a series of other elements until a stable nuclide is formed. Regents reference table N shows a variety of radioactive nuclei in the first column. Under the decay mode column, the Greek symbol for the type of particle released during natural transmutation is shown. You can compare the symbol to the symbols shown on reference table O to determine the particle release from the nucleus. Alpha decay occurs when an radioactive nuclei has too many protons. The nucleus breaks off 2 protons and 2 neutrons, producing the new element. Beta decay occurs when a radioactive nuclide has too many neutrons. A neutron is converted to a proton and an electron or beta particle is released from the nucleus. Positron emission and electron capture both occur when the radioactive nuclide has too few neutrons. Positron emission occurs when a proton is converted to a neutron, releasing a positron from the nucleus. Electron capture occurs when an inner atomic electron is absorbed into the nucleus, converting a proton to a neutron. Artificial or induced transmutation occurs when atoms of an element are bombarded with particles in a nuclear reactor or particle accelerator. All transuranium elements are man-made through artificial transmutation. The equation below shows an aluminum nuclide being struck by an alpha particle to produce the new element phosphorus and a neutron. Nuclear reactions can be expressed as nuclear equations as shown on the previous slides. Nuclear equations use isotope symbols to represent each particle. Reference table O has the symbols for a variety of particles such as alpha particles, beta particles, neutrons, protons, and positrons. Notice in the equation below, both the total mass number on the left side of the equation is equal to the total mass on the right side of the equation. 222 equals 4 plus 218. Also, the total number of protons on the left side is equal to the total number of protons on the right side. 86 equals 2 plus 84. During nuclear equations, the mass must be conserved, and also the total charge must be conserved. On the next few slides, we will practice writing nuclear equations. Alpha decay occurs when there are too many protons in the nucleus. Write a balanced nuclear equation for plutonium-239 emitting an alpha particle when it decays. We begin with the symbol for plutonium. Plutonium Pu with a mass of 239 and an atomic number of 94. Arrow will produce an alpha particle, so it's a symbol for a helium nucleus. It has a mass of 4 an atomic number of 2. Plus, we're going to produce a new element. To determine the new element, we use the idea that the total mass before the change must equal the total mass after the change. So 239 must equal 4 plus an unknown number. 239 equals 4 plus 235. We also know that the total atomic numbers on the left and right must equal. 94 equals 2 plus a number. 94 equals 2 plus 92. Now we look up on the periodic table for the atomic number of 92, and we write the symbol for the element, which is uranium. This is the complete equation for the alpha decay of plutonium-239. Write a nuclear equation for iodine-131 emitting a beta particle when it decays. Beginning with the symbol for iodine, we have a mass number of 131 and an atomic number of 53. Arrow, and we write the beta particle, which has 0 for a mass and -1 for a charge, plus the new element. Now, 131 must equal 0 plus a number. 131 equals 0 plus 131. 53 must equal -1 plus a number. 53 equals -1 plus 54. And looking up on the periodic table of elements, the symbol for the element with an atomic number of 54 is xenon. This is the complete equation for the beta decay of iodine-131. Write the balanced nuclear equation for potassium-38 when it emits a positron from the nucleus. We begin with potassium-38. Mass number 38, atomic number of 19. Arrow, and we write the positron symbol, which is a positive charged electron with a mass of 0, plus our new element. 38 must equal 0 plus a number. 38 equals 0 plus 38. 19 must equal +1 plus a number. 19 equals 1 plus 18. Now we look up on the periodic table for the atomic number 18, which is the argon atom. This is the complete equation for the positron emission of potassium-38. Write a balanced nuclear equation for silver-106 capturing an electron. So we start with 106 for the mass and 47 for the atomic number. Now we're going to capture an electron. So we're going to have the electron on the reactant side, plus the electron with a mass of 0 and a charge of -1, makes the new element. Now, 106 plus 0 must equal the mass on the right-hand side. So my mass on the right side must be 106. 47 plus -1 must equal the atomic number of my new element. 47 plus -1 is 46. Looking up number 46 on the periodic table of elements, and we get palladium. This is the complete equation for the electron capture of silver-106. Now, when using artificial transmutation, we still have the total mass on the reactant side must equal the total mass on the product side. And the total atomic number on the product side must equal the total atomic number on the reactant side. So to do a nuclear equation for lithium-6 being bombarded by carbon-12 and releasing a neutron, we would begin with lithium. Lithium has a mass of 6 and an atomic number of 3. Now when it's bombarded, it's on the reactant side. So we write plus carbon with a mass of 12 and an atomic number of 6. And it releases a neutron, which has a mass of 1 and a charge of 0, plus our new element. Now the total mass on the reactant side is 6 plus 12, which is 18. That must equal 1 plus the number on the product side. So 18 equals 1 plus 17. 3 plus 6 on the reactant side must equal 0 plus a number. 3 plus 6 is 9, must equal 0 plus 9. And the number 9 on the periodic table is fluorine. This is your complete equation for the artificial transmutation of lithium-6 being bombarded by carbon-12.